Hello everyone, and welcome to the NEATEC Electronics Series. This episode is about high-frequency amplifier response from the field effect transistor amplifier. So let's get started. Alright, so let's talk about an FET amplifier, high frequency response, right? So what I did right here is I redrew an FET amplifier, right? Now this shows all the capacitors and all the resistors, right? And you have a capacitance right here, right? Draw it there. There's a capacitance, right? Why don't we call that C1? And we have another capacitor here, which is your output capacitor. We'll call that C2, right? Now, we're talking high frequency response. So remember, at high frequencies, these capacitors basically don't have any reactance. So there's no impedance to current flow. So those basically can go away and be replaced with a wire. So let's draw this again, shall we? So we're going to keep your source. Why don't you all do this along with me, because it will help in your understanding. The more you draw it, the more intuitive it's going to be, right? So we have what's called RS, that's your source resistance, right? RS, usually that's very small, most of the time it's neglected. Then you're going to come over here, you're going to have a resistor to ground, call that RG. Now you're going to come over here. Notice we got rid of the capacitor there, that input capacitor C1. We're going to draw your FET. Here we go. Here we go. Now your source is going to come down here, be connected to ground. Now, remember that your VDD is going to be thought of, you can think of it as an AC ground. So that's actually a ground, right? And very similar to how it's exactly the same as how we did with the bipolar junction transistor. If your voltage here is VDD is determined to be ground, is AC ground, basically, you can bring this over, and that's going to be going to a ground, right? Even though it's AC ground, it's still a ground, so that's RD, right? Then you're going to go through a capacitor, C2, but guess what? We don't need to include that, do we? Because we're talking high frequency, right? That can go away. And then we're going to come down through another resistor, which is RL, right? But guess what? These two are in parallel. So what we can do here is simply, instead of R capital D, we'll just call this RD, and that's going to equal, what's that going to equal? It's going to equal RD in parallel with RL, just what we just said, okay? Now, you have internal capacitance here of your device. That's going to be what really matters. So remember, you're going to have a capacitor here, okay? That's going to be CGD, gate drain. You're going to have a capacitor here. That's going to be CGS, gate source, CGS. Alright? And you're going to have CDS. I'll come down here. There's enough space. That's CDS. Alright? That's not so bad, right? Now look, here's the deal. These values of capacitors are not given directly. You have to infer them. So in the data sheet, you're not going to see these, right? At least not right now. So you're given other variables, which then you can use to calculate these values, all right? So you're given these variables right here. You're given C, I'm going to write them down here. CISS. Alright? That actually stands for your input capacitance. Alright? You're given CRSS. And that's going to equal the reverse transfer capacitance. It's a lot to write, isn't it? Reverse transfer capacitance. That's a single T, A, N, C, E. All right. And then we have COSS. And that's equal to the output capacitance. All right? These are the values that you're going to find on a data sheet. Now, when you have those values, how do you calculate what your capacitances are? CGD, CGS, and CGS. So here you go. This is what you need to know. CGD, gate drain capacitance, right? That's equal to CRSS. Alright? That's this one. CGS, that's your gate source, right? That's equal to CISS minus CRSS. Alright? And finally, capacitance of your drain source, CDS, that's going to equal COSS minus CRSS. Alright? These are the equations you need to know to calculate those capacitances that I wrote up here in green. Alright? These capacitances, obviously these equations use these values which are given to you from a data sheet. And the reason why you have those values is because those are easier measurements for the manufacturers of the capacitors to make. The manufacturers of the transistors to make. I'm sorry, not capacitors. Alright? Now, this is very useful. And I am going to redraw this here. Alright, I'm going to take that away from you now. Now, let's redraw this. Okay? So, when you redraw this, that's basically going to be Here's your source. Going to go through your source resistor here. It's RS, right? Now, you're going to come out, and you're going to go to RG, right? Now, what else you think we're going to have here? We're going to have a capacitance this is going to be CGS, your gate source, right? Now, remember your buddy Miller? There's a Miller capacitance here. This was discussed in the bipolar junction transistor high frequency response video. Miller capacitance, this is what I'm talking about. So if you need a discussion of that, I recommend you head on over there and take a look at it. But this is a theorem which is used for high frequency capacitance of these the calculation of high frequency capacitance in these amplifiers. So then what you're going to have is you're going to have a C in Miller here, right? In Miller. All right? Let's draw that to ground. Now, I'm going to draw these. And this is your source. It comes right down to ground, right? So this just a tad over. Just a tad over. Alright. Now, here comes the output, right? Now remember, your output is going to be C out Miller this is going to be your capacitance of your drain source. And that's going to be, I'm sorry about that, let me redraw that line. That's going to be connected to this RD. That was defined right over here. Alright, this right here is your drain resistor in, sorry, it's just a D, in parallel with RL. Alright? So, this right here is your high frequency equivalent circuit after applying Miller's theorem. Alright? There you go. Now, let's start looking at calculating the input critical frequency and the output critical frequency. We're going to start on that next. Alright, so let's look at the input critical frequency here. And remember, this is for the high frequency. We already did the low frequency, so we're talking about the high frequency amplifier response. Specifically, we're looking at the input here for an FET, and we're going to be interested in this part right here. Alright? So basically the formula is, as many of you already know, right? FCU, that's upper, the critical frequency, right? Upper, not lower. That's going to be equal to 1 divided by 2 pi, and then we have an R and a C. Alright? Well, the trick is obviously figuring out the R and the C. So if you look at this, right, we're just looking at the input, really, is what we're looking at. You're going to have a resistance here at your gate, which is right here. I'm going to write that in blue, right? I think that's probably the best way to do it. I'll call it R in, that's a gate. Alright? You're going to have right here resistance right here, RG, right? And you're also going to have RS. Now look, the trick is to find the resistance across the leads of the capacitors, right? So if you Thevenize this, right, that means you make a short out of your source right here. You can basically redraw this below, and that's what I'm going to do now. This is going to be there's your source, it's a short to ground. You have RS right here, right? Then you have here, this is RG. Then what are you going to have next to it? All the way over here you have R in gate. I'm just going to put all the resistors together. R in gate. Got it? Now over here you're going to have your capacitors, but we're just looking at calculating the resistance right now. So if you notice, all of these are going to ground, aren't they? RS is parallel with RG, which is in parallel with R in gate. So look, your R in gate, this is going to be extremely high. Very large. Alright? We're talking, it could be in the giga-ohms, high mega-ohms. It's very high, right? Your gate here, RG, is also going to be high. Alright? That could be in the mega-ohms. Mega-ohms, high kilo-ohms. But your RS is going to be relatively low. Now look, if you have resistors in parallel, the current's going to tend to go through the least resistance, right? Obviously current, I think it's Kirchhoff's law, but the current coming in a node, it's going to distribute to these resistors, but all the current has to go somewhere and to ground, right? But in this case, we're going to estimate that since these resistances are so high that it's all going to go through RS. So in many equations, you're going to see the formula that's RS. That's basically your source resistance of your source, right? That is why that's RS, because this resistance is much lower than RG or the gate input resistance, all right? So what we can say, I'm going to just write it down below here for you. So you can say Rn is going to be equal to Rs in parallel with Rg in parallel with R in, and here's your gate, which is approximately equal to Rs. And that's why you have an RS right up here. Alright? Now the next step is to determine your capacitance, right? What's your C going to be? Well, the capacitance basically for this is simply going to be your CGS your gate source capacitance plus your C in Miller, which is right, obviously you got your CGS right here, and you got your C in Miller right here. So you sum them up, and that's your C total for your input. But that is your capacitance. All right? Now remember, your C in Miller, this right here, that's going to be equal to CGD, right, gate drain, times AV, which is your gain of your amplifier, plus 1. As you can see, this input capacitance, since it's simply multiplied by that gain, and gain is usually a larger number, this has an effect, right? This is an important calculation, so make sure you think about that when you do it. But it should be larger, right? Because if your gain's 200 or something like that, it's 200 times that value, it's going to give you a larger capacitance, all right? So that is basically, I'm going to rewrite this over here better for you. It's 1 divided by 2 pi RSC. And this C comes right from there. Now, let's do your output, all right? If you're looking at your output, you're going to look at this part, right? So basically, as we discussed previously, your 1 FCU output is going to equal 1 divided by 2 pi, again, RC. Now your R is right here. That's basically going to be what we call RD up here, right? It's just your drain resistor, your drain resistor in parallel with your load resistor, right? So I'm going to put a little RD there. All right? That's basically what we're doing on that one, all right? Now, the capacitance is something I wanted to make sure that we understand. As you can see, if we come back over here, you have CDS in parallel with C out Miller. But here's the thing. CDS is not specified in all data sheets, all right? So many texts will say that sometimes it is not designated. So in such cases, you must either assume a value or neglect it. So what we're going to do is neglect it. So this is basically going to be, where's my thing here? This is going to be C out Miller. All right. And what's your C out Miller? C out Miller is going to equal C, your gate drain, times AV divided by, AV plus 1 divided by AV. Now look, if AV is a large number, I don't know, 1,000 or 100, suppose it's 200 or something like that, 201 divided by 200, basically this is going to go to 1, right? So it's simply equal to C from your gate drain, all right? So that's how you calculate it. And your RD we already talked about. So that basically is how you calculate your input and output upper critical frequencies for this kind of amplifier. Now remember how to calculate your capacitances. This is the difference, right? There's several differences. They're similar to the bipolar junction transistors, but they're not exactly alike. But just remember those earlier equations. You can calculate them from parameters known as CRSS, CISS, and COSS. COSS is not always specified, and you need that to calculate CDS. That's why you either have to assume a value or neglect it if it's not specified. All right, everyone.